Good morning, everyone. I'm Dr. Reza Said Kandezi, and today we are gonna talk about the JTAG boundary scan standard using the IEEE 1149 Part 1. And today is not just talking about the standard, but we are gonna talk about how it works, why it's invented, these JTAG boundary scans testing, and have a understanding of what it would affect the manufacturing, the uh, testing and validation, the debugging, all those things that relate to the digital electronic system. Now, let's start with the context. In the 1970s and 1980s, basically the digital logics started to kind of like evolve very rapidly. All the device that once was use a deep component or deep packages and had like 8 to like 16 pins were replaced basically by PLCCs and QFPs and even eventually BGA packages, and all of them kind of like had like around like hundreds of pins. And beside that, the PCB design also evolved, and instead of like having like a two-layer design, we have now like four, six, or even 10 layer design that basically makes all the system very dense. It is help us to gain more performance, and basically that density is also a plus, but it comes with a trade-off, and the downside is the access to the pins and the parts components in the circuit. So we don't have a direct access to necessary signal anymore. So this rise of the complexity basically and multi-layer PCB make those parts or those components basically inaccessible for physical props. So this transition from the uh, true hole component to the SMT component basically eliminates the pin leads that we had through the board. That what that means? That means that the manufacturing test that relies on a like a bed nails, fixtures, oscilloscope, or logic analyzer, which all of them require a direct physical contact with the PCB traces or like a component pins. All of them are now out of the picture. So if there is any faults happening or any soldering defects uh, exist in our PCBs or in our components, it becomes very hard to detect them without having an invasive probing or even like using expensive like kind of like X-ray inspection. So because of that inability to observe the internal signal states, basically industry demanded a solution that would basically scale with complexity. So we wanted to like eliminate the dependency on a physical access, okay, and make it an automated kind of like testing process. Now, this is when JTAG standard, or like what we talk this case in this discussion, the IEEE 1149 Part 1 was developed and basically expanded to address these needs. So we could have a testing, we could test the digital system, analog system, and mixed signal systems, and solve the problem that we have for the because of that increase in the complexity and density of the circuits. Now, IEEE 1149 Part 1 originally was published in 1990. So because of the ambiguities in wording and implementation practice, it needed to like have a revision, and it needed to be edited. The In 1993, there was a revision or the amendment for the IEEE 1149 Part 1 that tried to like help with the ambiguity and define some critical elements of boundary scan. We are going to talk about what it means, the boundary scan. And basically, the most important addition actually that revision was the introduction of the BSDL, which is the boundary scan description language, the protocol of that testing that we are talking about, which basically that language is a machine readable file format that basically defines how a chip implements the boundary scan, and it includes like the pin functions and the scan chain structure, all those components that we need for the JTAG testing. Uh, in this family of standards are not just one part. The IEEE 1149 has several different parts. Like for example, we have the part 4, which discussed the mixed signal test, and basically was developed to extend the boundary scan testing to analog and mixed signal component on the digital ICs. We have the part 6, which is the highest speed differential interconnect testing, which addresses a specific problem, which is the traditional JTAG cannot test the highest speed differential link like LVDS or HDMI because these links are AC coupled. So the standards add new logic elements that can generate and detect the special test patterns on AC coupled lines. We have the IEEE 1532, which is the in-system programming, and it was developed to apply a standard in the system programming of the programmable logic devices, the PLCs, the PLDs, uh, like FPGAs and CPLDs. And the standards basically support full programming flow, including erase, write, verify, and security features like authentication. And but this standard that 1532 is very crucial for file upgrades and remote maintenance, especially when the systems cannot be physically accessed. Okay, so we have also on IEEE 1687, which is the IJTAG, and it was developed to access the embedded instruments inside the integrated circuit through basically a reconfigurable scan network, which unlike the fixed scan chain in IEEE 1149 Part 1, which is we are gonna talk about that in upcoming slide, the IJTAG introduces a dynamic routing, okay, for accessing different instruments based on the configuration of that testing. Uh, now, now that we know the history, let's talk about the adaptation of this JTAG by the industry. Now, the JTAG standard was used in the industry, and it was essential. But why it's considered essential in modern electronic? Let's kind of like break it down to basically the three key aspects of that, why it's important and why the industry adopt that standard. Basically, this IEEE 1149 Part 1 is implemented in virtually all modern digital ICs, including microcontroller, microprocessor, or FPGAs. And basically, the semiconductor companies use that JTAG circuitry in their chips so they could have access for testing, to have the testing access without needing physical props or even extra pins. Okay, so uh, like FPGA vendors use JTAG not only for testing, but also they use that for system programming and configuration of their board too. So basically, the semiconductor industry heavily relies on JTAG for both manufacturing test and runtime actually debugging mechanism. Okay, then we have a board and system level vendors. It's not just a chip. We have JTAG has a broader kind of like application when we're talking about the board and system level. So the original equipment manufacturer, original design manufacturers basically used and integrated a JTAG to their board level validation and testing. So that standard actually basically enabled them to have automated board level testing within the manufacturing line to verify the inter-chip connectivity. Okay, so if there is a defects in assembly, they could detect that. Uh, that system level test actually can be reused across different manufacturing stages from the prototype validation to the production line testing. So it is very useful for those vendors. It's also used for in-circuit programming of non-volatile devices such as like a flash or EE proms. So as a result, basically this JTAG become a very important and essential tool for maintaining the quality, reducing the cost in high volume production, and validating the performance and the quality of the product. Now, one of the kind of like obvious aspect of why the industry adopt that is the for the compliance bodies and like the certification bodies. So it become that JTAG standard, become a reference. So the industry standard basically become published by different organizations based on that JTAG testing. So like for example, in safety critical industries like aerospace, automotive, or telecommunication, basically JTAGs becomes a mandated test, and it is also a mandated debugging interface. Okay, so certification bodies, all the regulators, the auditors, basically require a proof of boundary scan test using the JTAG test protocols. Now, we talked about briefly about why IEEE 1149 Part 1 was originally developed. One of the problems that it addressed is the complexity, the increase in the complexity in the digital system and the PCB design, the multi-layer structure of the PCBs, which basically ruled out the traditional testing because all those traditional testing needs, as we said, physical access to all the pins and traces on the board. So this complexity basically avoid that access for the manufacturer and the validation vendors. So we needed a new method to solve that, and its solution basically created by developing the IEEE 1149 Part 1, which basically introduced a scan structure embedded inside the digital ICs. So it's a new paradigm of like testing. So it's not an external testing, it's actually embedded inside the ICs. So normally design places a flip-flops and logic cells at each input output pin, and it forms like a shift register chain. We are going to call it a boundary scan register, which allows each pin to be observed and controlled serially through the small number of test pins. Okay, so the test access port, which we call it tap, uh, basically is one of the modules, is one of the concept within the JTAG testing and acts like a gateway for external equipment to inject their test data, the test vector, and basically read the output. Okay, capture the values and see and evaluate the pattern, and based on that, detect the problems, the fault, and debug basically the system. Now, the outcome of this standard, okay, was that the boundary scan became a fundamental component in digital device. Okay, JTAG become the foundation, not only for test, but also for programming and like secure hardware configurations. All those parts are used by the JTAGs across the electronic industry. Now, let's talk about what is the boundary scan architecture that we're talking about. So basically, boundary scan insert a scan register, okay, which we call it the boundary scan register BSR between the all the input output pins of a devices that and its and their internal core logic. What that means? That means every pin, it doesn't matter if it's input, output, or bidirectional, has a dedicated scan cell. Okay, these scan cell act like a digital tabs that can intercept or inject logic values, and they are connected serially to form like a shift register. So they are cascading with each other, each after each, and it's like a shift register that the test vector go through each cell that are connected in series one by one. So this basically forms a boundary scan chain. Now, uh, this architecture basically allows a serial access for all the input-output pin and basically give us both control and observation from the outside. Okay, so the scan pass connects the test input, which we call a TDI, to the test output, which we call a TDO, uh, passing through all the scan cells. So using TDI, we inject a test vector, the data. It goes through all the scan cells that each pin in our device has one scan cell and they are connected in series. It goes through all the scan cells one by one, step by step. And then we read the values from the TDO pin, the output, the test output pin, and then we analyze it and we find out, okay, for each pattern of inserted test vector, what is the result of monitoring the data? Like for example, if two of the pins are short-circuited with each other, okay, if we inject several type of test vector, we are going to see that in all the configuration, these two pins always have the same values no matter what is the configuration of the test vector. That means that like those two pins are short-circuited, or if like one of the pins is short-circuited to ground, no matter what is the vector, the test vector that we inject in the TDI, what we read at TDO is that that pin is always zero. So that means, okay, that pin is short-circuited to the ground, and like this is like a debugging test and a fault detection that we are talking about. Now, let's talk about the core components in this architecture, as you could see in the some of them in the slides. As we said, we have a boundary scan register BSR, which is a shift register, basically that includes all the scan cells that capture and apply the values to the input-output pins. We have test access port, which is we call it TAP, which is a physical basically interface, which we basically can scan and access and control the whole circuit inside the chip. We have a tap controller, which has like a 16 state, finite state machine, okay, and basically manage the execution flow of the scan operation. Okay, so the tap controller manage the whole testing process. Okay, we have an instruction register, okay, IR, which select which internal register. It could be the ID code, it could be bypass is currently active during the sequence. Now, uh, we talked about the boundary scan cell. Let's go into that. Everything basically in JTAG, from testing pins, observation, interval state, basically relies on these scan cells in the boundary scan cells. But what is the boundary scan cell? The boundary scan cell is a small hardware, okay, implemented between the device core, device core logic, okay, the functional part of the IC, and all the input output pins. Okay, it captures basically the signal values for each pin or internal logic. Okay, and it could inject or override those signal that's going to the pins. So not only we could inject a test vector into the pins to debug or test the system, because it's connected, the cells are connected to each individual pins. Basically, it could capture the output of the core logic in the normal kind of like condition when it's actually in the functional mode. Okay, so it is gonna be a little bit like it's not a real-time observation. It has like a because of the structure, it has like a delay of getting the data, but it gives us also a good observation capability. Now, there are types of boundary cell. We have input cells that uh, basically connected between the input pins and the core logic. Uh, it contains a shift logic that allows the captured value to be inserted into the scan chain. And during the test mode, the input cell basically can block or override the signal from reaching to the internal core logic. So we would avoid the unintentional kind of like behavior in our chip. We have output cells, which again sits between the core logic output and the output pins, uh, which basically could bypass the output signals to come directly from the core logic. Uh, when system is in a normal mode and in test mode, these scan cells takes over and force the output pins to a specific logic level, those test vectors that we're talking about. So we could have control test patterns applied to those output pins. We have bidirectional cells, which basically is combine both our input and output cells. These are the pins that these are connected to the pins that are used both for input and output kind of like purposes. Now, the A scan chain configuration is basically uh, the configuration of that boundary scan cells that we're talking about. But what is that scan chain? Basically, as we said, all the scan cells are connected serially. So this scan chain is the serial interconnection of all those scan cells in boundary scan cells. Okay, so this change for a boundary scan register, and basically you can think about it as a shift register made up of a 1 bit per pin. Okay, input output pin. So these BSCs, those boundary scan cells, are linked basically head to tail in a linear path. So they are in series. Okay, so and it allows a serial access. So we have overall configurations, okay, which is it means all the cells inside the device are serially connected. We said that it gives us the full scan path, begin from the TDI, the input, the test data in pin, all the way through all the scan cells through the output, the test data output pin. Uh, that TDI is basically the pin that serves as an entry point for all the test data, all the test vectors, and basically our test data enters from the TDI to the uh, scan chain and travels through all the scan cells. We have a shift operation, which we said because the scan cells are in the series, we have like a shift operation that uh, uh, let the test data that is injected from TDI pass through each scan cells. And this happened. This is not a haphazardly shift operation. So it has a clock that synchronizes all that. So each pulse of the clock would shift the data from one cell to the next one. So uh, basically, this clocked pipeline makes sure the precise timing and synchronization of all the pins in the scan register. Now, we have cell contribution, the aspect of the cell contribution, which basically means the scan cells contributes exactly 1 bit to the overall scan chain. So each cell has 1 bit input output. So we can see what is the condition of that pins. So this structure basically allows all the engineers to construct and basically apply a complete test vectors and map all the input output pins states inside our chip. So after all these configuration, we have a TDO. We talk about that. This is like a test output pin, which after the value goes all through the cells, through the chain, we capture the result from the TDO, and these captured values basically are diagnostic result and is extracted bit by bit and typically sampled by an external test equipment to basically verify the correct behavior or check the state of each pin, like the example that we said, like short circuited to ground or short circuited, two pins are short circuited to each other. We could get that from the data that we capture from the TDO, which all of them, like TDI, that clock that we say TC, we call it TCK, test clock, and the TMS, which is the test machine sequence, and the TDO, the output, they're all in the closed loop of the full boundary scan configuration. Now, we have several operational modes when we talk about the boundary scan. Uh, uh, and during those modes, the boundary scan cells behave differently. which is basically controlled by the tap state machine that we introduced earlier. Uh, we have normal mode that the boundary scan cells are completely bypassed. So the chip works as intended. We don't conduct any test during that mode. We have the test mode, which all the boundary scan cells become active and intercept and control all the pins, all the input output pins activity. So that's when the test data injected, and we are gonna try and shift that test data bit by bit using the clock pulses through the scan cells and read through the output and check the state and the behavior of the all the pins. Uh, all the output cells in this mode are override and basically drive a specific test patterns to external nodes. And uh, this mode basically give us a precise control in all the digital pins. We have observation mode. In observation, as we said, that this boundary scan is not just for testing. It gives us also the ability of the observation. So in that mode, in the observation mode, those scan cells are passive. So they just capture the data. So the core logic of the chip works in their normal functionality, and the pins having their states as it intended to do to do their jobs, and those boundaries scan cells act like a observer, like a measuring point. So we could capture all the datas, not at real time, but the values that arrives in each input output pin during the normal functionality of the chip. Now, switching between these modes are controlled by, as we said, by the tap state machine. Okay. Uh, we also call it a tap controller. It's a 16 finite state machine that is defined in IEEE 49.1. It basically controls and transition the whole boundary scan condition between these three modes, and basically these. But you have to like pay attention to that. It is these transition, the signal of transition that is introduced by the tap controller are all deterministic and synchronous. So it precisely says the control over when and how the boundary scan architecture is set and invoked. Now, there are three fundamental operational states for the boundary scan cells, uh, which one of them is capture, another one is shift, and then opted in capture, we have values. I'm sorry, I put real time is not a real time. Actually, it has a delay, not much, but it has a little bit of a delay. We capture the values from the pin or internal logic, so providing a snapshot of the device state. In shift, we basically is the same as we talked about earlier. Uh, the clock, the TCK that we have, basically introduce some pulses. Those pulses are triggering a shift between the scan chain. So it's basically push the data bit by bit through the all the scan cells that are connected in series. We have the update state, which basically in updated state, the last bit shifted into each scan cell is transferred from the shift register into the output latch. Okay, so this mechanism basically allows the device to apply test vectors to its external input output in a synchronized and deterministic manner. Now, These boundary scan cells interact also with the device internal core logic. Okay, so this is where the scan chain transition from the pin level interface to internal signal control. Okay, why did that matter? Why this matters? Having this interfacing to the core logic, basically, is just not. It allows the boundary scan to not be just an interact with the pins. Basically, they sit between the pins and the core logic, so it has like a bidirectional interface. It becomes a bidirectional interface that prevent interference with the normal operation, allows the test data to flow through the through the scan cells without corrupting the core logic functionality. And also, as we talk, the observation kind of like aspect of these boundary scan cells enable a invasive diagnostic over the core logic of our chip. Now, when we design and basically implement these uh, boundary scan cells, okay, there are some challenges uh, uh, in the process. So even though the IEEE 1149 provides like a standard for functionality, the physical integration and scan cells, but still we have some constraint like timing, layout, and even like tooling that we have to address. Okay, so the timing constraint basically uh, talks about the fact that all the boundary scan logic should be designed so it doesn't violate the setup and hold time requirement of the internal core logic. So for example, any signal crossing from the scan cells into the core logic or vice versa must be preserved with the clock domain integrity and data stability. Okay, so failure to address these timing constraint basically result in a logic failure or during a certain scan configuration appears as like a defect in the functionality of that core logic. Now, we have a clock domain crossing constraint because the basically the boundary scanned register operates under clock domain, that TCK that we talk about, which is independent from the system's functional clock. So basically signals that crosses from the functional domain into the scan domain or vice versa, they all should be properly synchronized. So we don't have a meta stability problem. So if we don't manage this clock domain crossing, it would lead to the data corruption or missed test vectors or false failures. Okay, so when we have a multi-clock systems, uh, each individual BSR section needs to be partitioned or gated so it would accommodate the domain specific constraint. Now, we have the constraint over the insertion of the automation. These tools that are used in a modern kind of like digital design basically support automatic insertion of the boundary scan cells. So basically they rely on that boundary scan language that we talked BSDL, and although it reduced the design effort and minimized the human error, and manage naming convention, pin association, or control routing, uh, designer should specify all for which input output pins receive these cancels, or allowing the customization of the test coverage. So without these automated tools, the large multi-million gate devices can be fully scanned with this automated tool, can be fully scanned with a minimal manual efforts. Now, the effectiveness of the boundary scan depends on the strategic placement of those scans. So when we talk about the high test coverage, it means that the most of, if not all, the most of the critical input output pins and internal nodes are basically reachable through the scan pass. Okay, so if we have a proper cell placement, basically it enable us to detect all the failures and faults and even logic bridging for both device and board level kind of like inspection, audit and inspection. Now, let's kind of like talk about a summary of what we so far gone through. We talked about the self-diagnostic system, which basically we said that the boundary scan architecture transform the integrated circuit into a self kind of like diagnostic device. So we have the test and observation logic embedded directly into each input output pin. So this mechanism supports automated testing, real-time diagnosis, or failure isolation at device level. And we also have the testability in the board level. Uh, these JTAG and those boundary scan architectures basically give us a virtual prop. So it each scan cells replace a physical test equipment. So we don't. It is basically means we are probing all the nodes, all the critical nodes, without actually physically invading those nodes with the invasive kind of like probing or expensive kind of like X-ray scan that we talked about. Now, these boundary scan registers could be act as a programmable data bus that basically interfaces directly with all the pins. So we could use a serial loading specific data patterns and drive a control output and receive controlled input. Okay, so uh, these boundary scan provides the foundational basically infrastructure for advanced test, debug, and in-system programming techniques. So this is also what we so far we went through, and the boundary scan architecture is basically is not an option anymore. As we said, it's mandated, and it's one of the elements basically when we design any digital system and any complex like microprocessor, microcontroller, or even SMD layer, multi-layer PCB. Now, let's talk about uh, a little more about the TAP or test access ports. Uh, you can think about that TAP as like a gateway to the entire boundary scan structure. Okay, all embedded inside the digital device. So this basically tab is a minimal hardware interface. Okay, normally is like 4 or 5 pins that give us the boundary scan register, internal instruction and data register, and on-chip debug and test infrastructure. Basically, when we use the tab, we get to inject test vectors, we get to observe output and control scan operation, and have an interface with a core logic for diagnosis and configuration audit. Now, the tap signal test in the defined in IEEE 1149.1 basically are used for uh, tap controller for the finite state machine, the scan chain, that BSR, the instruction and data register, and ultimately the entire boundary scan test infrastructure. So basically a standard that we are talking about, the IEEE 1149 Part 1, defines a minimal tab interface uh, with 4 mandatory signals and 1 optional signals. Okay, so uh, those 4 mandatory signals are TDI, TDO, TCK, and TMS. TDI, as we said, is the input, so it's a serial input to the device for the testing modes or debugging modes. TDO is the output when we observe the behavior of the all the scan cells and the pins, and even we could like monitor the operational behavior of the core logic. The TCK is the clock. This is mandatory. It's control all the tap states and the shift between the scan cells, and basically it synchronized the whole process. The TMS is test mode select, which basically, as we said, we have several state for the tab, that normal mode, the test mode, and the observation mode. This TMS basically controls the transition between all those states in a tab controller. The optional point, the pin that we talked about, is the TRST, which is the test reset, which is basically an asynchronous reset for the tab controller. It is optional, as we said, and uh, uh, unlike the TMS, which requires a sequence of 5 rising edge on the clock to reach the reset, it can reset the tab instantly and basically very reliably. So is not implemented. If it's not implemented, the tab reset is normally performed using the TMS. There is a 5 consequence of 1, the bits equal to 1, like 0, 1, but the 5 1 bits basically from the TMS means the reset. So you can use that, or you can use the TRST to just use 1 signal, 1 bit to reset the tab controller. Uh, the tab state machine that we talk about, and it has a 16 state finite state machine inside it. Basically, it controls the tab controller, basically governed by this state machine, finite state machine, and it is a sequence of instruction through a well-defined kind of like state transition. We have a test logic reset, which forces the device into the safe condition. We have update operations, uh, which basically load new values into the system. We have shift operation, which moves the values from cell to cell using that clock pulse. We have run test state, which is like a test execution state. We have select scan pass, which is basically defines the state branch to either data or instruction register pass. We have a capture state, which basically loads the current values, the observation that we talked from the selected register, so we could like observe the functionality of the core logic. Now, for the tap timing that we said is very important factor in the uh, test process. Uh, the setup time is the basically the minimum time that we need to uh, align the TDI and TMS, and all that should be stable and based on the rising edge of the clock. So each clock pulse defines the timing of the test. If we have an improper alignment between the data and the clock signal, it is result in a wrong state transition or corrupted scan data. So for optimal timing, basically it's common to align the TDO sampling with the falling edge of the TCK. So the TDI works with the rising edge, TDO works with the falling edge. We have the signal integrity when it comes to the electrical design of the tap, and it's in order to maintain a clean signal and keep the TCK trace short, the clock trace short and most isolated to avoid the crosstalk between the clocks. We have a power domain design, so all the tap signals should operate in the same voltage. So if we have a not properly level shifted between the domains, we are going to have a floating values during the power up or debugging session, which basically cause an unpredictable behavior and a wrong kind of like a result in our testing. Now, this is basically so far we talk about the JTAG. We talked about why it's important. We talk about how it works. We talk about the process of the JTAG, all the definitions, all the parts of the JTAG, what are the constraints, what kind of electrical design we have to consider for the best practice of the JTAG. So if you have any question, please let me know. Otherwise, thank you for your attention.